everyone. Welcome to the algorithm seminar. Today we're happy to have Clayton here to give a talk. He's an incoming final year PhD student at Columbia studying machine learning theory. His work focuses primarily on the representational properties and the inductive biases of neural networks. He has additionally worked on solving learning combinatorial algorithms with transformers as a Microsoft research intern this summer, and climate modeling with ML as an Allen Institute for AI intern in summer 2022. Please welcome our speaker.
Hey, well, thank you everyone for having me. I'm excited to be here and excited to be at Google. Just to check, so everything's perfect. Hopefully everything should be fine Zoom-wise. And I'll be kind of talking into here and also kind of looking around. So we'll see how it comes out video-wise.
It's Google Meet.
Sorry. Well, I was embarrassed earlier because my talk's in Keynote, and I realized that like these are my Google Slides, but it's not in Google Slides. So hopefully that's not a big faux pas. But anyway, yes, thank you for having me, and please jump in at any point with questions. I'm happy to talk about things, and also as we get into it, this work is kind of a choose your own adventure where like I have several theorems, I have several proof ideas, and I'm happy to spend more time on proofs that people think are interesting and less time on ones that people don't. So please make your preference if you say what you think, ask questions, and all that. So yes, this talk is about transformers. In particular, it's about like what various transformer architectures can do and what they cannot do in terms of neural network representation. So you might be familiar with this type of work in the context of like standard neural networks, like depth separation type results, where like certain neural networks can efficiently represent some functions and other ones cannot. And this is trying to take some of those ideas and work with them in the kind of new field of transformer approximation. So I imagine most people here know what transformers are, but I'm just going to briefly define them as in the form that I'm going to use them in for this talk. So the fundamental unit of a transformer architecture is the self-attention unit, which you can see on the side right here. And what we're going to think about the self-attention unit being is basically this matrix product between the input sequence X multiplied by a query parameter matrix and a key parameter matrix, and then multiplied together, and then passed through the softmax function, and then multiplied with another corresponding value matrix that goes along with this input. So critically, this is a sequential model. So we think of like X as some, say, passage of text, maybe, where we have maybe the passage is n strings long, and each of these we can think of as being represented by some like d-dimensional encoding. So like for the purposes of this talk, we're going to think of n as being much bigger than b, like in in the context of GPT-4, where we think of like the context length n as being like 32,000 characters long or something, or 32,000 tokens long. So something very significant. And then these model parameters are d by m, so m we could think of as like the embedding dimension of the model. You then can attach multiple of these units together in parallel into multi-headed attention, which in this case, we're thinking of this as you have capital H different units, you add them together, and then you also add, maybe we're thinking about having some like residual connection where you add the input X to that sum. And then in between layers, we're going to have what we refer to as element-wise multi-layer perceptrons, where we take each of these d-dimensional functions and we apply some multi-layer perceptron, which we're just going to think for now about as like some arbitrary function mapping a d-dimensional input to another d-dimensional output. And critically, this is applied individually to every sequence element. So when we do this, we have tremendous representational power, but we're not allowed to do this to the whole sequence all at once. The sequence elements can mix within the context of self-attention, but they can't mix in the context of MLPs. So what is a transformer? Well, transformer is an application of these units in sequence, where we take the input, pass it through an MLP, pass that through self-attention unit, pass it through another MLP, and compose this, in this case, d times, where d is the depth of the model. So we have a few key model parameters, the depth d, the width or the number of heads h, and then the embedding dimension m. So these will kind of be the key parameters we talk about when we talk about what it means to efficiently represent or not efficiently represent. So as I mentioned before, one of the key questions we're going to try to answer is whether by using this function approximation method, like so by proposing functions we can learn or can't learn. Can we use this to show the representation, show the powers of certain types of architectures? And in particular, one question we might ask is like, how do these compare to other types of neural networks we use? Like these have largely, transformers have had most of their success in a lot of their success in NLP, where they've largely supplanted approaches like recurrent networks. So like, can we come up with target functions that illuminate the strengths of transformers over, say, recurrent networks or fully connected networks or general MLPs? And then also, can we specifically talk about these parameters in a more fine-grained way? Like, can we talk about functions that require h to be small, or maybe require having a higher depth rather than a higher width? How can we talk about the interplay of those? And then finally, the last thing is like, can we come up with tasks that transformers more broadly fail to do or struggle with? So to put broadly, what our contributions are is that we propose two different theoretical tasks that we think that we think give partial answers to these questions. And I'll give the caveat that, like, this is a theory paper first. Like, there aren't a whole lot, there are a few basic experiments, but there aren't a whole lot of experiments. This is mostly just like, we found these tasks because we think they say interesting things about these questions and about these quantities. But I think there's a whole host of empirical work that you could do alongside this. So the first task we coined is something called sparse averaging, which I'll define in detail. But basically, that this is a task which is easy to do with a transformer. Indeed, it's easy to do with a single unit of attention. And it's hard to do efficiently for recurrent networks and multi-layer perceptrons. And also it has this key interplay of this quantity m, that as the embedding dimension increases, the amount of averaging I can do increases in tandem. And then the other thing we do is we introduce these two different tasks, which could be generalized to be an infinitely many sequence of tasks. Where basically like this challenge of finding two pairs in a sequence is deemed to be easy, and this challenge of finding triples in a sequence is hard. And I can talk a little bit more about what that means later. But this is the key high level. So before I go into my results, I want to talk a little bit about how I think these exist in the world of other works on transformers, because there is increasingly a body of work studying what transformers can do. First, is there some works that have been done assessing the Turing completeness of these models, which are saying, if you're allowed extremely high numbers of parameters, can we simulate Turing machines? Can we simulate finite state machines? Maybe in this case, I think for a lot of the Turing machine examples, they're thinking about like literally simulating the tape, where you need a new layer of computation for every step of the Turing machine simulation. So it's a highly inefficient model, but also highly universal. Another way of looking at it, because this is like a very broad thing that shows the powers in the extremal cases, but doesn't care that much about actually having tractable models that anyone could ever expect to learn in the real world. The other way of looking at it is saying, okay, let's think about more constrained environments, and let's think about the types of tasks that they actually seem to do in practice. So this is work that tries to formulate the strengths of transformers in terms of like formal language tasks. So one example is this Dick language task, which you can just think of as like interlocking parentheses, where something belongs to the language, basically if like the parentheses and brackets line up right. So for instance, you couldn't have like open paren, open bracket, close paren, close bracket. Like that would not be like properly nested. And there have been some results that have shown that that these are learnable, but only that these can be represented with transformers, but only if they have some type of like bounded amount of recurrence that can happen. And critically, this, the previous model of transformers didn't care at all about transformer size. You were allowed to have really, really big ones. And in this ones, they're typically saying like, does there exist a fixed transformer that works for arbitrarily long sequences? Where like the question is, where like, you can kind of procedurally generate these types of languages using some type of grammar. And then it's a question of like, would a single model whose parameter count does not scale with the size of this of these instances work for that? And they drive some lower bounds, like this paper in particular, that you can't do that in the worst case. But that relies on this fixed size assumption. That like on some level, like it's not surprising that we can't always do these complex recurrent languages if you're not allowing the model to grow with sequence length. Separately from the sphere of representation, there's also a good amount of work, or actually the beginnings of work being done on more learnability-oriented results, where it's hard to analyze how gradient descent works for this. So instead, they're saying, okay, what if we are trying to do some learning task where we do empirical risk minimization on a transformer? How many samples do we need to generalize? They have these covering numbers type bounds, and then they say, okay, if we have these transformers, if the parameters are bounded by a certain amount, then you need this many samples to learn it. And then here are some concept classes that you can represent efficiently using a bounded number of parameters. Hence, these are tasks that can be learned using this framework. The harder question then is optimization. How do you tie that into gradient descent? And there's been the beginnings of some work on that show convergence of gradient descent for transformers. This is a recent paper by Spencer Fry and some of his collaborators at Berkeley that I need to read myself. But it's like proof of gradient descent convergence if you have if you're doing like least squares regression within context learning. And then finally, this paper doesn't get into it too much, but I think there's some decent analogies between what we talked about here and graph neural networks. And there's some interesting theory that I think has been proven about graph neural networks that could be related to transformers. So one of these things is that you can frame a graph neural network as kind of a message passing algorithm in a way, and there's an equivalence to this communication complexity or distributed computing communication model called the congest model that's been formalized there with graph neural networks and been shown to show the limitations of those. And we'll draw on that during the latter part of this talk. And also there are these relationships that have been drawn between graph neural networks and different types of isomorphism testing, where isomorphism testing is this theoretical problem that can be used to separate some graph neural network architectures from others. And this will also be analogous to some of the stuff we do today. So now that I've kind of gone through the background, I want to jump in a little more to talking about the results, and then, yes?
The HAF22 paper is just finite versus infinite separation, or is there more like quantitative color to it?
I don't think there's as much of a quantitative color to it. I think it's showing that, I think it's saying that there's no single transformer that can represent potentially Dick languages with potentially unbounded number of recurrences. But I'm not super familiar with the paper, so I could be
That
wrong.
itself is not super surprising.
No, I don't think it's super surprising either. And there are also some lower bounds in this paper with Christos Papademetriou and Binghui Peng, who I think is or was a Google intern, about that showing all lower bounds against the bounded depth setting. And like the key quantity they run up against is like the precision of the numbers, that like if you're trying to have these extremely long length sequences, eventually you run into precision problems if you're trying to do this with fixed architecture. And I think in their case, I think you were allowed, I don't think it had to be fully fixed. I think there's some loosening of the architectural constraints. Yeah, good question. Any other questions, I guess, before we move on?
Can you tell us more about the GNN graph automation testing results?
The graph isomorphism one?
Yeah, like the last line.
Yeah, so I think there's some papers that suggest that if you have certain types of graph neural networks, there's an equivalence to be drawn to this like WL GNN testing. I don't remember exactly what
the limitations, like, yeah.
Yeah, and I think what they do is
I think I know. I remember what you're talking about.
Yeah, but they introduce different orders of graph neural networks, so they're allowed to like have like basically like edges versus hyperedges, and basically I think as you increase the order of the GNN, you're able to do more sophisticated WL testing.
Mm-hmm.
And I think the WL testing is not like is kind of a partial graph isomorphism test where it'll catch certain types of non-isomorphisms, but not all of them. And as you increase the degree of this test, you can better differentiate them. All right, so I guess briefly before I get to my results, I wanted to talk briefly about kind of some of the modeling decisions that inspired it. One of the main things we can gather from looking at some of these model parameter counts of some large language models is that basically the context length tends to be a lot longer than the number of parameters that you have in a given unit of attention, which is one of the key things we're trying to emphasize here, is that like in the example of GPT-3, you have like roughly 2,000 character contexts, but you only have like h heads in a layer, you only have 128 dimensional embeddings. So like what we're thinking about within our framework is that you kind of have, you're allowed to do pairwise computation in a unit of self-attention, but you're sort of limited in how much you can express there. Like you're limited by the fact that this that the embedding dimension is much smaller than your context length. That you can't really treat this as a universal, as a way of getting universal computation, unless you have these quantities being large. And then the other thing which we use to kind of justify our modeling assumptions is that the MLP parameters tend to be really big. Like in this case, you have a lot more MLP parameters than you have in the context length. So that's sort of the reason why we model these MLPs as being arbitrary functions. So in this case, we think of the bottlenecks as being the self-attention units and the extremely expressive parts being the MLPs that can be applied to single elements, but not to the whole sequence. So now I want to introduce the two tasks we do and talk about some of the results, and then we can go a little more in depth into some of the results and what they mean and how we prove them. So the sparse averaging task is one of the tasks that we do, and this is intended to show the expressive powers and limitations of a single unit of attention. So what's the task? Well, we're going to think of the input as being a sequence of pairs, where the elements yi I'm going to think of as a q length subset of the integers between 1 and n. So n is the total length of the sequence, and basically each yi is going to tell me a subset of the other sequence elements to pay attention to, and then the zi's are going to be vectors. And the key idea here is that the task is going to be to output an average of zi's for each element, where the chosen indices are chosen according to this yi. So basically, it's a sequence mapping task where each input says average together these other inputs and output that. So in the key idea here is that each one is saying a different thing. So this is kind of a visualization of what the task is doing. We have these z vectors at the bottom, we have these y connections above it, and then we get these averages out. So what do we have? Well, basically we have that if we're trying to represent this task using a multi-layer perceptron or using a recurrent neural network, it's not going to be an efficient representation. And by that we mean that there's going to be some polynomial dependence on the sequence length n, which we're trying to avoid. Like we're trying to ideally have something that doesn't need to scale dramatically with the length of the sequence. So in the case of MLPs, you'd have to have a high width, a width growing with n times d. And with an RNN, you'd need to have at least an n-bit hidden state that gets passed between recurrent units. Both of these are relatively basic. I'm not going to actually talk about them much in the talk. Yes?
Is that the zj or zi?
Where?
Like for the function, the
The output RHS.
the QS, like how is j used in the function?
Oh, sorry. Yes, this is a typo. That should be a zj. My bad. Yeah, sorry about that. Yeah, so right, this is the ith element of the sequence, and it will be an average of q different elements, and it's averaging zj for each one. So thanks for that. Sorry. So then what we have is that if you're looking at transformers, though, this q parameter is significant for what's the minimum we need in order to represent this. So critically, if the embedding dimension m is more or less larger than q, then there exists a construction that does it. And if it's a little smaller than q, then we can prove using a communication bound that there is no construction that does it with a single unit. So this is sort of like the main result that I might talk about in this section, but that we get this key dependence between this task and the parameter and the size of the network needed to do it. So this is sort of part one, and then part two is this difference between pairwise and triple finding, where instead we can think about the input as being an n-length sequence of integers between 0 or 1 and m. And what we're going to do is we're going to have the first function is basically going to ask, are there two numbers in the sequence, including the one that I'm looking at right now, that sum up to 0, mod m. So for instance, the ith element of the sequence is 1 if there exists some other j such that xi plus xj is 0, is m or is 0, and if not, then it's 0. And then match 3 is basically the same exact thing, except that now we're saying, are there 2 other elements such that all 3 of us add up to 0? So in here, what we have is we basically have a way of separating between these 2. So there's an easy way of representing match 2 with a single unit of self-attention. But we can't efficiently do match 3, even with a single layer, even if the layer is very wide. So essentially, the theorem is that you need to have either the embedding dimension grow linearly with n, or the number of heads needs to grow linearly with n. Like you basically have some dependence of that form. But we can do some type of generalization, kind of like the higher order graph neural network generalization that exists, where you can then show that this match 3 problem becomes easy once again if we're allowing ourselves to have this more generalized tensorized attention approach. And you could indeed keep doing this if you wanted. You could define match k and show that a k order tensor can represent it. Like I think it's most interesting I think in this simple crystallized setting, but you could generalize it beyond that. So that's the high level of what. And then I also have like a conjecture here that I think it would be hard with a deeper network too. That like I think if you have more than one layer, I think it would still continue to be a hard task to do match 3 with a standard transformer. But that's more of a conjecture. We have some kind of corroborating theorems that correspond to it, but we don't have an exact. We don't quite have the proof that we would truly want for that yet.
And like, I just make it like 1 and 3 are easy, and 2 is hard to prove. Is that?
Yeah, I can talk about the constructions for 1 and 3. I mean, none of these are super hard to prove. This is based on communication complexity, and these are both. You can write it out pretty simply with like a constant dimensional embedding that relies on trigonometric. It just like applies trig functions to the inputs basically. Like they're pretty easy flowcharts that'll show why they're true. So I guess I want to step back and stop and see if there are any questions before I talk about some of the results in more detail and talk about the broader proof intuition.
Can you go back to the previous slide? Just this was like more clear. Again, like here, you like if you want to give a high level, the inefficient represent. So like the first result is like a hardness that you get out of like communication complexity logarithms again, or not?
So I think the first one I think is just like a simple rank based argument. But like if you have if the MLP is not low ranked, or if like the first layer of the MLP is not high rank, then you'll lose information and there exists some input where you won't be able to compute this function directly. But the RNN argument is by communication complexity, where basically what you do is you look at the bits between the first half of the task and the second half of the task, and show that basically you have to memorize the inputs from the first half of the task if you want to have any hope of solving the problem.
Mm-hmm. And like the second one, I don't know if you're going to talk about, but is it like simple?
The proof of this?
Yeah.
I'll talk about this a bit more. Yeah, I think it's the upper bound is like a little more is easy in principle, a little harder in application, and the lower bound is also like a communication complexity thing. I think it's like half of the reason I'm given this wrote this and gave this talk is because I think the results are interesting, but the other half is because I think the communication complexity has somewhat of a story to tell within the world of transformers, and like my knowledge of that stuff is pretty basic. Like I'm using pretty simple tools, and I think that people with a more sophisticated tool set in that area could say some really interesting things about the limitations of these models.
Sorry, so if it's like a communication argument, then then it should also apply to transformers too. So like I'm not understanding like how it goes around the lower bound.
So the reason why it goes around the lower bound is because in a transformer we sort of are allowed a lot of communication because we're allowed to basically do this mixing with the pairwise matching, or sorry with the self-attention unit. You're basically allowing like elements in the sequence to talk to other elements in the sequence. via like taking a bunch of inner products and adding them together.
Okay. Okay.
Whereas in the RNN case, because you have to do this in sequence, that does kind of mean like there's a point where you have to have a high dimensional hidden state in order to pass something from one layer to the next. So I think the critical thing is like this isn't talking about memory. Like you do have to, like any application of running a transformer will always require at least n bits of memory. Like there's no getting around that just by it'll require at least n squared bits of memory. But you may not need that many parameters to do this. Like you could potentially have a transformer that does this using far fewer than n parameters. And that's kind of the tension we're trying to get at here.
I see.
Thank you.
Is there any like separation results that shows that MLP or RNN is better than transformers?
Well, what?
I mean the other way around. So here you show that there is no efficient representation with MLP or RNN. So
Yeah.
Can one design a problem that MLP or RNN are better than transformers?
I think you probably could. I think one way of thinking about this with the RNN at least is like, transformers are kind of good at sparse long range connections, but they aren't actually good at like doing things in sequence. You can imagine like, a function which takes the first two elements and hashes them together and then hashes that with the third element and so forth. And, you could pretty easily implement that using an RNN, but it would be extremely hard to implement with a transformer. So like, I think these definitely exist. Like, it's not like a transformer is like a globally better model than these in every single way. But the transformer has nice sequence learning properties for NLP and other tasks. And this is sort of a way to say like, what if we get some tasks that are like vaguely sequence learning inspired and try to draw some conclusions about what that might be and how that might work. Okay, so I'll talk a little bit about part one, and then we'll get to part two. And I may skip over a few parts of the second result. So what I want to first do is talk about the positive result for representing the sparse averaging task using a transformer unit. And the key theorem we're proving here is that if you're doing this Q sparse averaging problem where you're averaging Q elements together, then the embedding dimension and our input vectors Z are d-dimensional, then the embedding dimension is basically going to grow accordingly with d plus Q log n. Where in this case, we're going to think about Q as being kind of the key parameter of interest. And we're to notice that there's a linear scaling of this quantity with respect to Q. One thing is because we're often talking about communication complexity here, it's kind of important for us to note the fact that the precision needed to do this, because all these communication lower bounds will break down if we allow real numbers that convey an infinite number of bits of information to go through. So one of the critical things here is that we only need log n bit precision in order to do this construction. So we're not relying on any real number cheats that we wouldn't be allowed to do with our communication complexity. And we can't get rid of this we can't get rid of this log n if we want to use infinite bit precision, but we're pointedly trying to avoid doing that. So how do we do this? Well, one way we can do is we can kind of take the idea of this task and break it down into what I think is the intuitive representation you would do with a transformer, and then show that is indeed possible to attain. So ideally what we'd like to do, and this is like an example here that corresponds to that one, is that we're saying each input is going to average over Q other different inputs. So one of the most natural ways we could implement that, if we were able to control everything in the model, would be to have the value matrix each correspond to the things you will be averaging over. So in this case, the ZIs down below. And then we want to have each element of the outputted softmax be either a constant fraction if it's to be zero if the element is not in the average, and 1 over Q if the element is in the average. Right, so this would be, in this case, the first average is going to average together Z1, Z3, and Z4. And indeed, we have the first row here being like 1/3, 1/3, 1/3. So that way, if you multiply this together, this will give you the proper output. So the main thing we're able to do here is that we can basically get this by ensuring by setting representation so that we could think of the key vectors corresponding to each of the things you're averaging together to be some like randomly drawn vectors, and then we deliberately choose the Q's to basically lie on the hyperplane spanning them. So we're going to think of this as like a high-dimensional polytope spread out in a lot of different space, and then each Q will critically lie on the face that correspond on the face that intersects with all the things it wants to average together. So that way, then this inner product, the inner product between these will all take on the same value, and then everything else will have a lower value. So then if you scale up the embeddings, then the softmax will ensure that these big ones stay big and everything else goes to 0. And this allows us to basically recreate this matrix. So then like from here, like this is like the key idea that shows how it works. The theory that we're sweeping under the rug is that you need to figure out how to draw these. So we do some analysis that relies on like the restricted isometry, on like using restricted isometry to show that these vectors must exist. And then like the input MLP is effectively like looking up in like using some lookup table to find which of these vectors apply based on that. So we have the vectors of this property. We use those to obtain an attention multiplication of this form, and then that allows us to exactly represent the target. So any quick kind of high-level questions about the construction?
So just picking random points in a sphere doesn't work, or?
It does. It does work. I think the main thing is that you have to. Yeah, it works. You just like it's like the analysis that's more tricky, because you need to then figure out like what's the minimum dimension where you can still get the property. And initially we weren't doing any of the restricted isometry stuff, and we were just doing it purely based on like concentration bounds. And that was causing us to have a Q-squared dependence. So the restricted isometry stuff was how we got it down to a Q dependence instead of Q-squared.
So the D in your problem is that ZIs are an R to the T, right? That is the D here.
What's that?
The D in this problem, sparse averaging, is that ZIs are an R to the T, right?
Correct. Yeah. Which we have to have if we're going to represent the Z's value functions here. So like, there's no avoiding this term, and the log n is the price we pay by doing the isometries with this with these randomly drawn vectors. And the key thing is we can get rid of this log n by if we don't care how big these vectors get. Like basically, we're able to bound the size of these vectors and of the number of bits we need to efficiently represent these. But if we didn't care about that, then we could get rid of this log n factor and just have it be p plus q. And that's based on, I think, like using cyclic polytopes for these sets of points. So this is a positive result. The negative. Oh, and then we found that if we train neural networks, they indeed do converge to something looking vaguely like this. So you do end up having attention matrices that more or less line up with what they're supposed to be over time. So if we have like in this case, the red squares are the things you're averaging together, and this is the number of epochs of gradient descent. And as we train longer, the squares that we want to be big end up being big. So how does the negative result work? This is where we use communication complexity. And the idea here is that basically if we're using log n bit precision, then the embedding dimension must grow according to Q. And we have this like divided by log n factor basically as a result of the bit precision. If the bit precision were something else, if this were p bit precision, then it would be Q divided by p. But it's generally, I think, easiest when we're contrasting our results to think of the bit precision being log n bits. And the key thing here is that once again, we get linear dependence on Q. And this is where our first communication complexity argument comes in. So what I want to do is I'll walk through this one, and then I think I'll probably hand wave through some of the similar proofs later, because they all rely on kind of the same set disjointness reduction. So just, I guess, quickly at the show of hands, like how familiar are people with basic communication complexity? Like, do people know what the set disjointness, like what set disjointness is and like what the communication complexity of that is?
You can always be reminded.
Okay, cool. So I'll talk about it briefly. So the idea of it is here, we have Alice and Bob, and let's say each of them has an n-bit string. And they want to ask the question of, are their strings disjoint? So in other words, is there any I such that AI is 1 and BI is 1? So if that were not the case, then Alice's ones do not line up with Bob's ones. And in this case, what we're going to think about is that the quantity we care about is not computation, but communication, and how much Alice and Bob are allowed to communicate. So basically, the protocol works where Alice can spend however much communication she wants, doing whatever she wants, and then she sends a single bit to Bob. And then Bob does the same and sends a single bit to Alice. And then the game is how many bits does it take them until they can compute this function with certainty. And there's a lot of work done on this, but the key thing is that you can show that for the set disjointness thing, it requires n bits if your list contains n bits as well. And you can note that there's like a pretty trivial protocol that allows you to do this directly. The protocol is Alice tells Bob her first input, Bob tells Alice his first input, but Alice tells Bob her second, and so forth. And then by the end, they know the entire other person's string, and they can just compute manually whether there's any disjointness. And it turns out you really can't do better than that. That like there isn't a better way of compressing down your string and sending it to the other party. So what we're going to do is we're going to do a reduction that's going to be powered by this approach. Where basically we're going to start out with, we're going to assume for contradiction that this doesn't hold, that there is a self-attention unit that has lower embedding dimension than Q over log n. And we'll show that if that exists, then Alice and Bob can create a protocol that uses fewer than n bits in order to, and allows them to compute this function correctly. So if they can, which must be a contradiction because we know by communication complexity that is impossible. So what I'll do is the proof basically consists of describing what that protocol is, and I'll discuss what that is. So suppose Alice and Bob start out with 2 strings. In this case, where I think n is going to be like their n is going to be the same as this n. And for the sake of simplicity, I'm making NB4. So what they're going to each do is they're going to each encode it into, Alice is going to encode her input into the y's, and Bob is going to encode his input into the z's. So the y's tell you what to average together, the z's are the things that you actually average together. So what Alice is going to do is she's going to ignore, I guess in this case, I think it's like more like n over 2. So in this case, like their string's length for the number of sequence elements is 9. So what Alice is going to do is she's going to ignore her first 8 inputs. She can set them to be whatever she wants. Who cares that we're averaging together there? And she's going to encode her last input to be, in this case, a sequence where if an element is 0, then the first 2 elements will be 1, 0. And if an element is 1, then the element will be 0, 1. So basically what she's doing is she's laying out which 4 things she should average together. And she's doing it by saying, okay, like my first input is 0. So therefore, I want to average the first input. The second is 1, so I want to average the 4th. The third is 1, so I want to average the 6th. And the 4th is 0, so I want to average the 7th. So there's a clear one-to-one mapping right here. What Bob's going to do is Bob is going to choose the different things that get averaged together. And basically what Bob will do is Bob will say all the even elements are going to be 0. And the odd element will be 1 if and only if the corresponding sequence element is 1. So Z1 and Z3 are 0 because these 2 are 0. Z5 and Z7 are 1 because these 2 are 1. So now what does this mean? And Z9, we don't care about that. So we're just, in this case, we're only looking at the 9th query. We're not looking at the 9th values. So what would this mean when we average it together? Well, it means that the only way that this average will always be 0 unless, because Alice only chooses even elements unless you have 1 here. Or sorry, Alice only chooses odd elements unless you have 1 here. And then Bob only chooses, Bob's evens will always be 0. So the only way this average is going to be anything other than 0 is if at least one of these things lines up. And the only way one of these things are going to line up are if the two corresponding sequence elements lined up in the first place. So in this case, if they can successfully compute this this Q-sparse averaging problem, then they can perfectly solve their disjointness. Then they can perfectly solve their disjointness problem, and we derive the contradiction. So now what we just have to do is we have to come up with what the actual how they're actually going to solve this. So we're going to assume that the model exists, and we're going to assume they both know what the model is. That's not really the hard part. And basically, what Alice is going to do is she's going to compute the query vector corresponding to just the 9th input. And she's going to send that to Bob. And then what Bob has to do is that's the only part of the network that Bob doesn't know how to represent. Like everything else, either he doesn't care about because these things are all fixed, or they're based on inputs that he does know for these z's. So if Alice sends him just the bits corresponding to this query embedding, Bob can compute the rest of the network because he has all the weights written down. So Bob computes the output, and then compares it to, and then asks is this first element 0 or not? And if so, he rejects, and if not, he accepts. So in doing so, they've shown that using MP or M log n bits, they're able to compute this function. So the only way this will not contradict this disjointness thing will be if M grows according to Q. So zooming out, does this make sense? So I think we have some other lower bounds which make arguments similar to that, and I'll probably talk a little bit about them before I wrap up. But this is kind of like all the lower bounds we do in communication complexity vaguely follow, or in communication complexity in this paper vaguely follow this format. Like we're not using any particularly insane communication complexity tools. It's just that if both actors know what the architecture is, they can compute an output that solves this disjointness problem, and therefore derives a contradiction. So thus we now have these two results that shows this two-sided dependence on this quantity Q. So this basically wraps up the results on this side. Before I finish, I want to talk a little bit about the high levels here, introduce the conjecture I have, then we can wrap up. So for match 2, I said before that it's easy to do, and I can walk through why it's easy. So basically what we're proving here is you can have a single unit of self-attention with a multi-layer perceptron input that represents match 2 exactly. And the way we're going to do it is I'll walk through an example which basically explains what the proof is. So if you have this example, what should the output of this be? Well, it should be 1, 0, 1, 1, right? Because 1 plus 5 is 6, and 3 plus 3 is 6. And in this case, we're allowing I and j to be the same thing, so 3 plus 3 is 6, and we have that taken care of. So what we're going to do is we're going to rely on this pretty simple trig embedding, where basically the query vector is going to map everything to the cosine of the input and the sine of the input, and the key is going to map it to the cosine and the negative sign. So what we're doing is we're basically mapping them onto the unit circle, one in the normal counterclockwise direction and the other in the inverse clockwise direction. And what this does is it gives us a nice property that that the query dotted with the key is going to be cosine of 2 pi xi plus xj. So what this means is that this thing is 1 if and only if the two things add to 0. There's an asterisk here because there's like an annoying detail that you have to work out, and the solution is you pad the sequence with an extra element at the end, but that's sort of unimportant. Sequences end with an end token. I think that's fine. So then if you have this, then this gives us the desired type of softmax matrix we want, where you have 1 if and only you have 1 in the 1, 3 column and the 3, 1 column, because these two things add to 1. You have all zeros here because none of these things add to 1. And then that will give us the vector we desire. So we can do this type of approach for this case, and it's pretty straightforward. The negative result, which I won't, I'll give the theorem, then I don't think I'll go into the proof in that much detail. But the key idea here is that if we now go to this match 3 problem, if we want to do it using a single layer of self-attention, where you have h heads and embedding dimensions m and log n bit precision, then the only way you can approximate this is if the embedding dimension times the number of heads effectively grows linearly in the sequence length. That there's no way that here you can have in the match 2 case you could have this be a constant, and here it must grow polynomially with the sequence length. So the key idea here is this is another communication complexity argument where we assume that there exists some model. And the main idea is here, instead of like Alice controlling the keys and Bob controlling the values, Alice is going to control the first 4 elements, Bob will control the second 4. Alice will we'll have some planted instances, so that the only way that this thing so that you can map the output of this one-to-one with the output of disjointness, and basically Alice will send Bob a partially computed instance of the self-attention, which Bob will again use to complete the network, or to complete the network's outputs. And the key thing here is that Alice's kind of half computation will only send roughly m times h bits. So if m times h is less than n, then you're going to again derive a contradiction, and they'll be able to solve the problem using this approach. So I want to talk briefly about this generalization, which is that here's how match 3 becomes easy if you allow yourself to have a higher order of attention. And the model we construct here is basically where instead of having a single key and a single query, we're going to imagine having two key matrices and 2 query matrices. And what we're going to basically be doing is taking the softmax over, instead of an n by n matrix, an n by n by n tensor. So it's a weird thing. It mostly exists like for the sake of argument, for the sake of showing that like this match 3 isn't some absurd function that you can never hope to approximate. Like I'm not advocating for anyone to actually code this up. But I'm arguing that like this standard attention unit is sort of ill-equipped to handle intrinsically 3-wise functions, and that this other architecture might be. And there are some analogies in the graph neural network literature, like the stuff on the WL testing, that defines these types of higher order graph networks. So I don't think it's totally out of line to do so. But the key idea is that if you do this, then you can again get back this constant embedding dimension construction. And it's basically going to be using the same type of principle. We again have these trigonometric embeddings so that the inner product for triple is going to be the cosine of the sum. And once again, you'll get that this is 1 if and only if all 3 things add up. So this is the same argument. You could continue generalizing this if you wanted to 4, 5, whatever. So we have some other results along these lines. We also, one thing you could also do if you zoom out is people might say, but we do triple matching when we have language models. Like you're able to, if I ask you to find like the subject, verb, and object, you could probably do that. Like, how's this a hard problem? And I think the key caveat there is that you have some type of, you have meaningful assistance there. Like you have context, and maybe you can link the subject and object, and then, or subject and verb, and then link that to the object or something. And we define a few notions of like assisted match 3, where you have some contextual information, it becomes an easy problem once again. So this isn't to say that like, the average instance of match 3 should be hard. We're saying that like without context, it's hard to solve this problem. So part of the reason why I'd love more sophisticated communication complexity people to take on this work is because my hunch is that it continues to be a hard problem if you have a higher depth network. Like I tried a number of times to come up with, say a depth 2 construction of a transformer model that approximates match 3 without, efficiently, without having these parameters growing according to n. And I couldn't come up with it. Someone else might be able to, but my hunch is that you still do need the parameters to grow linearly or at least polynomially with n, even if you're doing it with deeper networks. And we have some intuition for this. I think for the sake of time, I'm not going to talk over it much, but it relies on this idea that you can draw a connection between transformers and congest networks, and I think this problem would be hard to do with a congest network. I think it would probably be better to like either talk with me offline about this or check out the paper. But like we have some intuition that we think this should work, and we proved it for a similar problem where you can use other techniques. So looking at this on this graph models type problem where you have where you represent the adjacency matrix as sequence elements, and you're trying to find a 3 cycle instead of like this type of 3 match, then you can show that you need a high dimensional, or you need a high embedding dimension or high model parameters. But that's like a different problem. It's like a slightly messier thing, and I think I feel like it should be possible to translate some of these techniques to this other one. But I think my time is almost up, so I'm going to wrap up. I think so. Like our key work was to identify these 2 tasks and prove some things about their limitations and their advantages. As I've said before, I'd love to see if these results can be better fleshed out and better expanded upon using more communication complexity approaches. The flip side, I think, would also be interesting to look at this using more geometric approaches to see whether this dependence on bit complexity on bit complexity is actually necessary. Like there might be nice ways to pose problems that are hard to do with transformers, or that have meaningful separations without needing to restrict ourselves to having only p-bit representations. And lastly, I think there's also like a lot of empirical work that could be interesting along this lines. I think, the one of the key ideas that we advocate for here is that one of the key powers of transformers is this kind of sparse pairwise connectedness that both has a lot of power to do sparse communication or computation as the embedding dimension grows, and that also is sort of able to do sophisticated things with pairwise connections, but not necessarily with higher order 3-wise or beyond matches. And it would be interesting to talk with people who are more NLP minded about like whether you can connect this to some language tasks or other things that we maybe struggle with that are, intrinsically 3-wise or something. And then this is sort of along the same lines. Like, are there nice intrinsic 3-wise tasks that we struggle with? So with that, I want to wrap up and really thank everyone for having me, especially the Hub and Jiming for coordinating this. I had a great time, and thank you all.
I have a question. So for this kind of sparse averaging, so you prove for this kind of 1 layer of this kind of like a transform.
Yeah.
But like, what happens for multiple layers? Do you have a conjecture also for multiple layers? You still have similar thing for your conjecture as your conjecture for match 3, or you have like you can construct like a multi-layer transformer to compute this kind of sparse averaging.
I'm not sure. So I guess the question would be like, if you have more layers, can you do it using fewer parameters?
Yeah. So if you have more layers, because finally you have this kind of conjecture for match 3, right?
Yeah.
Do you have like similar conjecture for this kind of sparse averaging?
I don't as of now. I think. Yeah, I'm not entirely sure on. I don't really have strong intuition either way on that. Although I wouldn't be surprised if depth doesn't save you that much. Like I don't think there's. I would be shocked if there were like a 2-layer construction with, with like a total parameter count sublinear in Q.
So your conjecture is like we still need like the total number of parameters should be linear in the input size.
Well, not in the input size, because for that one, our results are not linear in the input size. Like this is linear in the averaging parameter.
Oh, okay.
Which I tend to be thinking of as smaller than n.
Sure.
I guess you could imagine this being n over 2. In which case, maybe, but I don't think you would. Yeah, my hunch is that the depth wouldn't help you that much, but I could be wrong.
Okay.
A question for the communication lower bound. So
Yeah.
I think the reduction, the core is like doing linear product, right? So have you tried to do the reduction from linear product in the product? Sorry. Because you may get some better lower bounds in the average case than the set disjointness, because set disjointness thinks about instance that's very adversarial, like probably never happen in real.
Yeah. So I think we probably could do it with inner product. I guess the trick is that like the instance we're embedding it in is still a pretty adversarial. Like even if even if the inner product instances are average case over distribution, like this still isn't going to represent like the average case over instances over QSA instances, right?
Yeah, but the problem itself seems to be if you use binary, kind of like inner product.
Yeah.
Yeah.
I'll check that out though. Yeah.
I mean, do you think that there is a formal connection between the congest model that you said it a couple of times and the complexity and the power of? So there was no like formal connection. It was all intuition, not like.
No, there is a formal connection. So you can, I think you can show that there exists that you can. There exists a specific congest graph that you can use to simulate any transformer in. I think the main thing,
like any lower bound that we have for congest model, just transfer. Okay.
Yeah.
And the lower bounds for congest model are. Yeah. Okay.
So the reason why I think it became tricky is because a lot of the congest model. So like what we want in a transformer is we want to have like a long list of inputs. We want each one to be pretty low embedding dimension. And most of the congest problems I know that are hard are things that rely on having like pretty dense graphs. You know, it'll be like it's hard to do, say, triangle counting, I think, under congest. But doing that requires like a graph with like n squared edges, which means that we think about the representation as being as like n bits per each of the n elements. And that's why I wasn't fully satisfied with our results on that front, is because like you can prove lower bounds, but they require these like really high embedding dimension inputs. I think we're getting kicked out.
Thanks.
Thanks.
Thank you.